Hello and welcome to my lecture review for the textbook, Internet and Web Application Security, 3rd edition. This is done by Jones and Bartlett Learning. Again, copyright, they own everything. This is their book. I'm using their PowerPoints. I'm just providing video lectures for my courses that are using their official book. The assumption is you own the book and you are in one of my assigned courses. The book ISBN number 9781284206166. Again, copyright for the Internet and Web Application Security 3rd edition by Jones and Bartlett Learning is owned and maintained by them. These are just video lectures on their official PowerPoints, so let's jump on in. Chapter 1, the Internet and the World Wide Web. So learning objectives are going to describe what the Internet is, the World Wide Web, and the impact on business and personal security. We're looking at data processing, information, kind of the differences, evolution of computers, personal computers, workstations, and computing in general. Looking at the Internet, early days, mid days, 2000s, even early boom, late boom, and what we currently have as the modern day World Wide Web. We're going to be looking at client-server computing, as well as virtualization and a little bit of cloud. Again, this is more just an introductory, not a in-depth review for those topics. So, data. What is it? So I'm going to grab my pen. What's interesting is when we look at data, normally I look at things as raw. For example, now I'm going to rewrite that. If I have this type of data, 5, 20, 20. Name Arthur. This is without any context, just data. Like, what is it? We don't know. But if we add a component or context to it, it's a sign-in sheet. Now there's context. Now there's something that goes, oh, okay, date and name, that's a sign-in sheet. So we can normally call that information. Information formally is the result or product of data that's been processed or contextualized, giving meaning to it. That's kind of what we do. So data is the fuel and the reason why we do computing, networking, automation, processing. We have it everywhere. It's raw, just raw things for us to able to put meaning to. So data versus datum. The term data is the plural of datum. Datum is something given or admitted as a basis for reasoning or inference. Datum is used as a basis for calculating and measuring. Again, that's super simplistic, but datum is the singular version of it. Now, are you going to have many people refer to it as datum? Probably not. It's going to be data or information. And sometimes you can have people interchange data and information, and they're really not the same thing. So, datum gets turned into data gets processed, given contexts, and it becomes information. And normally, we can do something with that. So here we have clients, a computer, laptop, tablet, and they can be sending stuff to and from the server that might house said information, or the server might be collecting information, depending on what we're trying to accomplish. Oftentimes, this is called a IPO model, input, process, output. Input, process, output. And it takes raw data, processes it, contextualizes it, and gives us an output. In this example, data to info. That's how this kind of functions. So that's our basic model, which we're going to be kind of referring to throughout the lecture videos. So evolution of computers and computing, we have honestly evolved drastically. 90s, we had bulkier, large computers, that were expensive. And now, tablets, smartphones, they have more computational power than early 90s computers. Not just that, the mobility component alone. The nice thing is, I'll grab my pen again, the tablets and the smartphones. What we don't even talk about is the connectivity. Things like 4G and 5G. Let's do that 5G again, 5G. What's interesting here is you can now take your mobile devices and work with high-speed internet wirelessly. So it's just interesting to understand that technology has increased its capacity, its capabilities, its communication speeds alone, wired versus wireless. And there's a whole separate argument of which is faster now and which is going to be overshadowing. Yes, I'm definitely the believer that a wired connection will probably typically be faster, less interference and things like that. But then there's infrastructure that requires the wired connectivity. So there's all of that argument that we're not going to go into in depth. But the fact that it has grown so much, so increasing our ability while decreasing the size. If you look at a mobile phone from the 90s, early 2000s to now, well, it kind of depends. Now our phones got so small that they started getting larger again. Looking at like the 2-screen like flip phones now, even though like that was the size of the average phone, 20, 25 years ago. And yes, I understand that's an exaggeration. The phones weren't that big, but they were definitely greater in size. And for the most part, they've definitely decreased in size. Computing is going to follow the basic IPO model. And computers, that's the machines, the people, the information, the data, the devices, that will provide that component to the IPO model. Now I said information, that's what we're going to be turning all of this into. The people, the devices, all of that, that's going to generate the data that will then be processed to make said information. So some of this is subjective. The author wants to focus on computers being, first one around 1940. We're not going to go into the conversation of ancient computers or ancient compute devices or anything like that. So, with the author's definition, we have first paper computer or punch card computer, and that was early 40s to, late 50s. Then we kind of moved into the second realm of just punch cards. Third form, we introduced the keyboard. Between the 70s and early 2000s, we ended up with keyboard, mouse, and other handheld devices. Pins for input. I know there's more than that, but that's all I could think of was pins. And the fifth generation would be early 2000s currently, and the inputs could be devices themselves. could be experiences of the devices, could be IoT or industrial IoT. And then the output would be, again, physical devices, USB drive, physical storage, CDs, DVDs, could be a graphical interface. Though part of the fifth realm, I'm going to assume, is it's looking more at the data that was being processed, so the output would be the information, scores, probabilities, percentiles, things like that. And all of that kind of led us to, the 2020 plus era with AI. And that definitely is more of a learning model for collecting information and doing things with. What is interesting is vacuum tubes. I actually had a project where I had to work with vacuum tubes in 2025. So there are still devices out there that still use vacuum tubes. So before there was internet, I don't know why some of this is relevant, but it is what it is. We had our first satellite orbiting space, launched by the USSR, the Union of Soviet Social Republic, I believe. The collaboration of Russia with its neighbors. It was in 1957, Sputnik. The schools have expanded their curriculum to include more chemistry, physics, mathematics. Government began grant programs to fund scientific research and development. We had NASA and DARPA. DARPA's a big one here, that actually looked at how to further communication. And DARPA formed to look into the advanced technologies, weaponry, as well as compute devices. Here's a photo, an illustration of Sputnik. It actually was not super big, but it was more of it was the first. Some of this is history. So in 1962, MIT scientists presented the idea of galactic networks of interconnected computing devices that can communicate with each other. And so you had the National Physics Lab and MIT develop the term packet, and that would be across a switched network of computing devices, which would be then called packet switching. And if you're not into networking, some of these are going to be over some people's heads. When you first start learning networking terms, we do discuss packet switching and packets. But for this course, understanding this is just a means of transmitting data. In 1966, ARPA project was launched, or ARPANET project was launched, which would be the precursor to basically our campus LANs and what we would then become known as the internet. 1969 was the first message sent between the University of California at LA, UCLA, to someone at Stanford. The message that was sent was login. So, when we're looking at kind of the devices, we had standalone devices. With ARPANET, we ended up with 2 devices, and then they slowly doubled. So in the 70s, 9 to 13 essentially. 71, we doubled from 9 to 18, and slow progress, just kept climbing. And now we have more compute devices than we have people. We have, I think, 5 compute devices for every single person on the planet. So here's a diagram of ARPANET. And again, this was not really a full mesh network. This was a basically ring network. And they kind of just rotated. So here we have the Stanford node. Here we have the Ames nodes. Here we have the Utah nodes. Illinois. So each of these PDP points are different nodes. Carnegie, Harvard, UCLA, UCSB, so Xerox. And what's interesting is, for example, with Carnegie, if the link is taken down, they just couldn't communicate. If some of these main links went down, it would mean that mass portions of the network, the ARPA network, would just be non-functional. Hence why we needed to develop better communication, which then was our future networking. Legacy of ARPANET, again, we had basic email in 71. We had basic protocols like Telnet, that'd be 72, and that provided bi-communication links between two stations. We had basic file transfer protocols, basic FTP, in 73, and then we had ISIS, the intermediate system to intermediate system protocol. That was basically our first major route protocol for routing IP messages. In 83, we had our DNS, or our domain name systems, that basically allowed us to move away from just education and government, and that allowed for name to IP translation. In 84, we had our OSI reference model being created, and that allowed us to have a conceptual framework for us to analyze and review material. Again, if you're into networking, this is where we get our OSI model. And then we had our NSFNet. This is a competitor network to ARPANET that essentially outperformed the older and slower ARPANET, and that became the granddaddy of today's internets. There's arguments of ARPANET versus NSFNet. In reality, these early networks were the foundation building blocks for our modern day networks. So they're all basically the grandfathers of our networks. The maturing network would then have to figure out how to take different types of devices and allow them to communicate, because early on we had things like AppleTalk or IPX. And in reality, we live in an interconnected world that we don't care what your device is. We want all devices to be able to communicate. And so AppleTalk and IPX could no longer be functional. So we developed a new protocol, TCP/IP. This is a family suite of protocols. TCP is also a standalone protocol, IP is a standard protocol, but again, it's a suite. This set a standard set of protocols for connecting devices, regardless of manufacturer. You have an Apple device and you want to connect to your brother printer? Cool. We could do that now. Before TCP/IP, we could not. The protocol is basically a set of requirements, rules, procedures, guidelines that basically dictate how a process will be performed. How do we take data and put it on the wire? That's essentially what these protocols did. Again, TCP and IP, and when we talk about our maturing network, we talk about the protocol suite TCP/IP, because there are more protocols than just these two. Application layer protocols like HTTP, FTP, email, POP, and SMTP, these were all rules that could be used to send application data. So, I keep saying application data. There's a reason for that. So this is things that our users interact with. These our end users interact with. UDP is actually a variation of TCP, or a transport layer protocol. So users do not interact with that at all. HTTP or HTTPS is basic websites, or secure websites in the term of HTTP. Make that a little clearer. Boop. HTTP versus HTTPS. Basically, it adds a security certificate to the HTTP, thus making it secure. All right, email. We have the ability to send email. That is SMTP. To receive email. That is IMAP or POP3. Again, we're not getting into the layers of, what exactly the protocols are doing. I just want to kind of keep it higher level. But I did want to point out that there are protocols for sending and receiving email, sending or receiving a website, sending a data file. Why is this important? Because if we look at a reference model, either the OSI or the TCP/IP reference model, we can see that there are layers of communication, and there's protocols that operate at each layer. The application is where we, users, interact with the systems. So that's HTTP, email, FTP, things like that. Everything below that is our network infrastructure. How do we get the data on the wire? How do we handle flow control? How do we handle error checking? That's these two. How do we handle communication addressing? That's at this layer. How do we take all that information, all the binary data, and put it on the wire, put it on the actual media? That's this layer. More commonly, it will be Ethernet or Wi-Fi. 802.11 is our wireless Ethernet settings. So again, we have breakdown of our communications so that they can be organized, so that when we're looking at how the data flows on a network, we have a good understanding of how that actually functions. So why is this important? It's so that we understand there's a process, there's a structure to our network. Then we also have the ability to link things at the application layer using HTTP, allowing for hypertext links. And essentially that allows us to put links in a document so that either it can link to itself or to other documents. Why would a document want to link to itself? Well, maybe you're doing a 200-page report and you want links in there so that the reader could jump to certain sections. That would be a hypertext link. Maybe you're doing a policy and you want to have it be able to reference outside sites. That would be another perfect example of why you might use these types of links. The early internet only had a few ISPs, internet service providers, and then they connected to the internet using a subscription service like AOL or Byte Exchange or CompuServe. And most of this was all text-based. You had a modem, and you had to work through that with your service provider. In reality, that didn't work very well. A lot of us had just analog phone lines, so if you want anything high speed, what they considered high speed, you would have to do like a broadband or DSL. And again, there weren't a lot of service providers out there. Now, we have a lot. Our ISPs, there's 7 main ISPs in the US, and those are the tier 1 providers, and then there are hundreds of them. Since we said internet, essentially how it's structured is we have tier 1, 2, and 3. You have the big guys, that allocate to the smaller guys, and the smaller guys allocate to the even smaller guys. The small guys are where our homes connect. If we're a large company, we might be connecting to a tier 2. And if you're, a very large company, very rare, they'll connect to the tier 1. But basically the tier 1s are the big guys that handle most of the internet traffic for our country. Verizon, that's one of the big ones. So not the only big one, but they are definitely one of the big ones. So, even in the early days of the internet, we still had this type of tiered system. And what you'd have companies like AT&T that would then start buying out tier 3 providers. At one point, AT&T had like Yahoo DSL, because it used to be AT&T/Yahoo DSL, or AT&T Roadrunner. So you had some tier 2 and tier 1 provider that just kept buying up the smaller providers, building a more robust network, building up reliability, and just growing and growing and growing. So here was the early interface, kind of what it looked like. It was all text-based. Here is our early modem, which was more of an acoustic coupler. You would literally put your phone receiver on the coupler, and this would allow the telephone headset to create the connection to our remote connections or our remote servers. We had our Ropers, Archies, and our Veronicas. Again, these were all systems that were designed early 90s so that they could grow. The Groper system provided a simple to use method for searching content on a remote server. The Archie search engine was basically the first real internet search engine used by Roper to maintain and index files. Veronica was the very East rodent operated network index of computerized archives, basically another search engine, but it updated its index in the forms of lists. Made it easier. We had our gropeware and hardware. Our gropeware was basically the calendar software, IMing, instant messaging, collaborative software, things like that. The hardware was like the monitors, memory, the modem, disks. Normally no animation at this level. We had our World Wide Web, and that was more of the idea of a mesh network patterned like a web. And that project was submitted W3 so that we could get what the start of our network, our internet would be. The web proposal referred to as a browser and not the network. You would have a web browser that would sit on top of a network that would allow for communication. And there were elements central to the future success of the web. Things like a coding language, HTML, a document identifier, UDI, and a transfer protocol for transferring web pages, HTTP. We had our first early web browsers like Nexus Browser, libwww browser, Mosaic. These were all early on browsers, but they were not what people would look at today as a browser. So here's an example of libwww browser, and again, it's more of a display text. Then we had our Mosaic, which started displaying more graphical content, and it could not really handle a lot of animation. It was more focused on text. That was a huge portion, is understanding that early web browsers were heavy text. Then we had this concept of the battle for the browsers. Netscape was released mid-90s, Internet Explorer also mid-90s, And then Netscape and Sun Microsystem jointly announced JavaScript, a programming language. Microsoft released Internet Explorer with CSS. Netscape released Navigator source code as Mozilla. Mozilla became Firefox. Apple released Safari in the 2004 range. Google released its Chrome browser in 2008. 2015, Edge. 2017, Mozilla released Firefox with Web Virtual Reality. And then 2021, Chrome released Manifest Extension Management. And again, they just keep growing. So the question becomes, well, which is the best browser? It is subjective. And you're going to end up with people that will argue this. I'm of the mindset of it really depends on what you're trying to accomplish. That dictates what browser you're going to use. So here's the extension of WebPage for Microsoft Edge, and it allows add-ons to be attached to your browser. So we have the World Wide Web, but everyone kind of forgets to, or doesn't realize that we have multiple layers here. We have Web 1, Web 2, Web 3, Web 4. We have the Deep Web, and there are nuances here with this. What's interesting when we're talking about the World Wide Web and understanding what the internet is, oftentimes we forget that there's actually a whole different infrastructure or an underlining web that most people don't think about, i.e. like the dark web. They're normally not going to be accessed by the average user, but I did want to bring that up since we are talking about the characteristics of the World Wide Web and the different variations of it, since we are going to be talking about Web version 4, which was more focused in the 2020s and newer. What's interesting is the dark web makes up a vast majority of the internet. Some say 80+% of the overall content is actually dark web content. Though you have to have a specialized browser to access it. Just like you would have a web browser to browse a website, you'd have to have some type of darknet browser to browse the darknet. Well, those are called onions or onion routers or onion browsers. The onion browser allows you to view onion sites. It's just a clever way of saying multi-layered, and it gives you access to what is known as the dark web. And that's kind of the limit of what we're going to discuss here. I just wanted to point out that we're only going to be focusing on the top 20-ish% of the internet, which will be the World Wide Web. But I did want to point out that there are other variations as well. So with that said, Web version 1 was very static content. It was a little bit more dated. It wasn't as common. It was web page content is retrieved from a file server. Web version 2, more focused on social networking like MySpace and Facebook, Snapchat, things like that. Blog sites, video blog sites or vlog sites. It's more user-generated encyclopedias, like Wikipedia and more. Web version 3 represents more of a representative transformation of the web into a large online database, looking at trends, looking at decentralization, looking at blockchain. Blockchain is more of a peer-to-peer decentralized and distributed ledger technology with assets that are able to record and store. It's scalable. Blockchain is available, mutability, secure, and more transparent. And we're going to get into blockchain in a later module, but it is kind of important to note. So the overall structure is more of servers in a single location. And if that single location ever fails, we have a single point of failure. The internet is constructed more of a decentralized platform, made so that if a location is down, it doesn't affect the entire network. For example, we might have Google servers on the East Coast and West Coast. If the Google servers on the West Coast ever go down, only the West Coast is affected. The East Coast still has their access. So we have options. So with decentralized web, we have no single point. That way, if a specific region goes down, we don't have to worry. We are not concerned with, West Coast is down. What ends up happening is traffic is just automatically rerouted to wherever availability is. So the entire purpose of decentralized web services is so that there's no single point of failure, thus eliminating that failure component. But that does mean added costs. So other portions is you can have decentralization, but that might now lead into personalization of a web experience. If you are located in Chile and you connect using those addresses, you might now get a Chile experience of the internet. If you're in China, you might get a Chinese experience. The geographical location of wherever you're connecting to might put different experience components on your internet access. And I use those examples because this does actually happen. You end up with different forms of filtering based off of your location. If you look at Netflix or Disney Plus, for example, two main streaming services, they actually dictate what movies are available in which regions and at which times. So if you are trying to access a movie and you live in the US, it may not always be available, but next day if you go to Chile, it might be available there. That's all I mean by personalizing the experience for some of these streaming type services. With that said, we can now talk about Web 4.0. Pervasive computing or ambiguous computing. This is a more symbolic interaction between computers and people, and they obscure the separation. What's interesting is for the first major time, we have more data being generated by compute devices than people. Because it used to be people would generate data, and then the compute devices would analyze. Well, now we have devices, industrial or standard IoT devices, that generate their own data. Now we have data making devices making more data. We have data about data. And so that's what it means by the separation between computer and human are kind of being blurred, because the human component was always the data generating component, but that's not happening. That does mean things like the internet and the web must always be on and ubiquitous. That's true. There always needs to be something happening. There always needs to be some data being generated, or components, or at least the availability needs to be there. Even if no one's accessing them, there should at least be access just in case. The web became a large integrated operating system with its own resources, so that they kind of appear to be more local. You have other types of systems like machine learning and AI systems that will use learning information from users to provide additional information or additional data. So information that users might be accessing or using, the machine learning will use that as data to be able to build their own data systems to be able to answer better questions. The web communication component with users conversationally, where devices technically not necessarily. Hardware and software advances make the web faster and more reliable, and we've already talked about things like wireless and wired. The nice thing here is scalability means it is just growing. So moving past that, we have things like advanced word searching. We have better search engines. We start seeing things like search engine optimization. So, how do we now have website content or customers using websites and looking at data analytics to help drive traffic to or from a website? So that's going to be our SEOs. This is the process used to increase the chances of a website being included in the first search result page, thus becoming more likely that a company's website might have additional customers. Most people are not looking on the second or third or fourth page. If you're not in the first few search responses, you probably are going to go well undetected. Some of the SEO methods are link building, tagging, content optimization, meta descriptions, keyword searching, just to name a few. Again, this is not a complete list, but it's a start. We have a brief history of our search engines. We have Archie and Yahoo and AltVista, then Lucas and Ask Jeeves and Google. And now most people use Google. That's what it is. Directory portals began during the web version 1. And the server, built off of the server side included and the common gateway interfaces, kind of, again, started all in that earlier stage. So the server side included an interpreted scripting language that was primarily used to merge the content of one or more files into a web page. Our common gateway interface is the function of HTTP, set of rules for processing that interprets the actions of a web page to interact with the web server or other based servers. Again, this is now getting to the point where we're talking about content displayness or reactiveness to a end user and kind of how they interact with the user through the browser. Examples of an SEO tag in a search engine: you might have a tag like Jarns and Bartlett Learning. You might have a URL. You might have metadata descriptions. So there are add-ons here that kind of help with the development of said content. So let's look at some earlier versions. This is Google from 1998. It's very blocky, very just clear, flat search engine. So the flow of the elements would basically be a browser that will send a HTTP request. Actually, I'm going to grab my pen so we can look at this. So you enter a browser, google.com. That request goes down. Server processes it, gets sent over to maybe a search response, comes back in, and then it is delivered. That's essentially the elements of our web server. So there are lots of different forms of client-server computing. A file server, an application server, a mail server, virtual servers, web servers. Those are all things that will serve a resource to a client, normally meaning a dedicated resource to those that need access to said resource. Web server is a common one. Web servers serve web pages. Application servers serve application or maybe application data. Mail servers serve email, and so forth. Now we can get into the last major topic, which will be virtualization and cloud computing. Virtualization is a concept of taking a physical host and allowing it to virtualize or create virtual devices using software. You can have a virtual hard disk, a virtual operating system, a virtual processor. So it's really just a computer inside of a computer. Then you can limit the resources of that virtualized computer inside your physical machine, or in this example, host. Normally we need a hypervisor, type 1 and type 2. Type 1 is bare metal, meaning you might have a server, and the type 1 will be sitting right on top of that server. Where oftentimes most users are most familiar with Type 2. That is something that's installed on top of an operating system like Windows. So a Type 2 hypervisor might be VMware Workstation or VirtualBox. Those are two of the common ones that are used pretty regularly. But again, the big thing here with a Type 2 is it sits on top of a operating system. So the user will interact with the operating system that will interact with the hypervisor. So why virtual machines? It allows you to set up a virtualized environment that would simulate or act like a non-virtualized environment. Let's say you want to test applications and you're worried that the application may crash. You might set up a VM and do all your testing. If it crashes, oh well. You only have to worry about that VM crashing, not the physical machine. The only real difference between a physical machine and a virtual environment is the physical machine has access to all physical resources. The virtual machine has access to what you allocate to them. So keywords, host and guest. So let's say we have Windows running on our physical machine. That would be a host. Let's say inside Windows we have VM1 and VM2 running. These are going to be called guest OSs. That way we can denote the separation of those machines, because they're not always going to be identical. So here it is again. We have our underlining hardware. We have our OSs. So this is more like a Type 1, or sorry, a Type 2. We have our host OS, and then we have our VMs. Where here we have our hypervisor, then we have our operating systems, and then we have our VMs. This is more like a Type 1. So, just like any other resource, we have virtualized storage, virtualized memory, virtualized processors. So, how this works is we allocate X amount of memory, and that portion of memory is only used by that VM. So the virtualized memory is stored on the hard disk, which of the host machine. The host will then use its main memory to process the data using the physical processors. The three main computer physical environments can become a single computer virtualized environment. So we might have 3 physical servers that are at a certain capacity. What we can do is we can turn that capacity and maximize it. We can get a beefier server and have that one server host 3 virtualized machines. So what's interesting is, could we, for example, change? Could we over-allocate our resources? Sure. Oftentimes, we are actually not using all of the resources of our devices. So what one could do actually is over-allocate resources with the hope of not all the devices are using all the resources at the exact same time. So, real example, 16 gigs. Traditional thinking would say that we need 48 gigs of memory. But maybe we have 40. The question is, how much of this memory is actually being used at a given time? Let's say that On average, we're only using, here we have 26 gigs used on average. Well, if we had 40 and we only are normally using 26, we're still able to allocate 14 more gigs. This is called over allocation and does definitely help in our virtualization. We'll get deeper in this in later modules, but I did want to point out that these are things that do definitely happen. Our next section is on cloud computing. Types of cloud are service delivery models or deployment models. Our service deployment models are private cloud, public cloud, or some type of hybrid. A private cloud is a closed access structure. Access is restricted to members of a group. A public cloud can be, in essence, a private cloud offered over a public network or like the internet. A hybrid is a combination of both private and public. So you have the private cloud deployment with the public cloud deployment with the private cloud restrictions. Again, options. So, simplified view of the elements in a some type of subscribed cloud model is you have a load balancer that kind of controls access and balances the load between the application. Now this is very simplistic. You just see a load balancer, application, and database. There could be hundreds of servers where this is spread among. But we don't know because, again, it's supposed to be transparent to us. We are not supposed to always know what the underlying hardware is. Our service models are things like software as a service, platform as a service, infrastructure as a service. So let's say we want an application. We want Microsoft Office, but I don't want to pay upfront $300. Well, we can do software as a service and we can bill, $10 a month for X amount of users. Instead of having to buy the full thing, we can just pay or rent it each month. That's an example of software as a service. Platform as a service is more of a commonly used to build specific programming and testing environments. That'd be too costly or time consuming if done in-house. Maybe you want to spin up a Windows machine, a Linux machine, and a Ubuntu machine. Well, you may not be able to. You can do platforms as a service and spin up whatever you need as you need them. Infrastructure as a service is basically the method of delivering the infrastructure, the servers, the storage, the networking components, to devices or resources as they're needed. With that said, these are not the only service models. We can have AI as a service, backup as a service, cloud as a service, desktop as a service, PC as a service, networking as a service, communication as a service, video conferencing as a service, cybersecurity attacks as a service. My favorite, ransomware as a service. You could pay a ransomware as a service company to run a ransomware against the target. And that's as a service model. And while it's illegal, it does definitely happen. Alright, so in summary, we talked about data processing, and information. Understanding the IPO component here. We talked about the evolution of computers and computing. We talked about the early internet and today's World Wide Web, and a little bit about the dark web. We talked about the architecture and the overall computing structure for client servers. And then we ended with virtualization and cloud computing. Alright, that concludes this video lecture for this chapter. If there's any questions, thoughts, concerns, or issues, please don't hesitate. Feel free to reach out. Thank you.